Okay, so welcome everyone to lesson 3 in our revision series, which is made possible by NETEX and Absolute X. I am Dr. Cerene Rathilal, and today I am going to be teaching you a bit more about Euclidean geometry. So to begin, what we're going to do is we're going to recap on what we had done in the previous lesson. So when we had started part 1 of Euclidean geometry. So what had we done? So in that lesson, I had introduced you, or I have mentioned the main concepts that one would have to cover in preparation for paper 2 when you were all preparing in term 1. So some of the topics that we had mentioned was Euclidean geometry, which is what we had covered partially. We also looked at proportionality of triangles, and today we're going to touch a little bit on similar triangles, looking at some of the problems that we're going to be answering together. Okay, so as we proceed with upcoming lessons, there may be an opportunity for us to discuss trigonometry as well as analytic geometry and some of the other concepts that you will be assessed on in your final examinations for paper 2. Okay, so let's remind ourselves about what we had done. So in that lesson, which we had held in March, I had gone through the proof of the proportionality theorem, which was stated here below. And of course, as you can see, this was last year's examination paper, 2021. And this question carried 6 marks. So it's important for you to know the statement, as well as have a very good understanding about how to prove the results. So if you've missed that lesson, please ensure that you go back to YouTube and you watch the recording that is already available. Okay, so then we had gone on to kicking off with the theorems that pertain to the section on Euclidean geometry. So one of those results was this result pertaining to a circle, of course, right, with a chord, as well as a line drawn from the center of the circle bisecting a chord. So we had gone through both directions of this result. We had seen that the forward direction and the reverse direction holds true. So it's an if and only if statement. So here, if we have a circle with center labeled 0, so let's begin by just recapping a bit. So we have a circle with a center 0, and we have that AB is a chord, right? So if it is known that AP equals to PB, right? So the lengths here are the same. So if I know that this is equal to this, then we can conclude that the line segment OP is perpendicular to the chord AB. And the converse is also true. If I know that OP is perpendicular to the chord AB, then I can conclude that that line is bisecting the chord, meaning that AP here is equal to PB. So that was just a recap because it might be necessary when we are answering further questions today. We had also gone through a few other results that dealt with angles at the center of a circle. And we had, if we recall, we see that the angle at the center of a circle, in this case occurring right here, is twice the angle at the circumference. So important results to remember. Okay, and another important one that's going to definitely come in handy today is angles in a semicircle. So whenever you have the triangle in the following way drawn in a semicircle, where you have the vertices of this triangle lying on the circumference of the circle in the following way, and where one side of this triangle is actually the diameter of the circle, then it turns out that the angle here, in particular angle A, is actually 90 degrees. So we refer to that as angles in a semicircle because this triangle lies in one hemisphere, or the semicircle of the circle here, in particular with origin 0 or O. Okay. So we then ended up answering a question that looked at some of those results. So we had seen an application of those things. And this was actually where we ended because we were quite limited on time. So today we're going to be going through a few more results that we require, and then we're going to go straight into answering questions. Okay, so I see there were some further comments in the chat box. Okay, they were in response to Renee, so all good. So I'm now going to continue. I hope everybody is on board and everybody can hear me clearly and we're all good to go. Right, so let's talk about results in particular with respect to tangents. So one of the important results that we will require today is actually the Tan-chord theorem. But before we get to the Tan-chord theorem, there's one further result with regards to a tangent. So firstly, what is a tangent? Can someone explain to me what defines a tangent to a circle? What does it mean? So I'll just look out in the chat box. Maybe you could quickly type up something. So while you're typing that up, let's look at the first case that we are looking at in here. We have a circle with a point A that is outside of the circle, right here. And then I have a line from this point A all the way to some point on the circumference of the circle labeled T, and likewise another line from this exterior point A to another point on the circumference of the circle labeled S. So I now see the comments have come through. So a tangent is a line that touches the circle at exactly one point. And I see those are the remaining comments have the same sentiment, so excellent. So this is what we're looking for. It is a straight line that would intersect your circle at exactly one point on that circumference. Okay, so that's what we've got happening here. So clearly we see that the line SA and the line TA are both tangents. I'm sure you agree with that. So this result tells you the following. Okay, so let me explain a bit more about how this table here is working. So this is the information that we are given, and this is the conclusion. And the last column is telling me why. So it's giving us the reason. Okay, so that's how we read off this here. So I hope that's clear. So I had just explained to you all of the information that was given. We have a circle and we have two tangents drawn from an exterior point to the circle. So we have SA and TA. So if the conclusion is, so if we're given this information that we have an exterior point with two tangents to the same circle, right, on opposite ends in this way, then we can conclude that the length of those lines, the length of those two tangents are equal. And the reason we can conclude it is because they're tangents from an exterior point. Of course, there are definitive proofs as to why this is true, but we do not have time to go through it. And so this is the information that I'm presenting you with, and we are going to apply it in the upcoming questions, right? So that's the first result. The second result that I want to bring your attention to is the Tan-chord theorem. So you could be presented with information in two ways for this result. So remember, this is what you're given, okay? So you'll be given a circle with a tangent, which is drawn to the circle at point T, as you can see, right? So we have a tangent drawn at point T. And as you can see, we have this line TB, which is clearly a chord in the circle. So what we can do is we can conclude the following. If we have this chord, and through the chord, we have that the chord subtends another angle at point C on the circle. So if we have this happening, then we can conclude that the angle between the tangent and the chord, which is this angle here, angle ATB, is equal to the angle at C. So it's equal to the angle in this opposite segment, and that is called the Tan-chord theorem. So it's telling you something about the angle between the tangent and the chord. And likewise, here, it is the same situation. So I've got a tangent and I've got a chord. In this case, I've got TB, which is the chord here. So the angle between ATB is equal to angle C. But of course, I could also view it in the opposite way. So here, this is still a tangent, and CT is a chord. So the angle here, subtended, so if I call this K, so KTC, so this angle is obviously equal to the angle in the opposite segment, and that is B. So I hope that that is clear. Did everybody follow that explanation about what the Tan-chord theorem does? If you're presented with a diagram, would you be able to identify a tangent, a chord, and the angle in the alternate segment? So please feel free to just pop in yeses and nos into the chat box. I see quite a few yeses coming through, so this is all good. So thank you for that. Right, so we will be applying it shortly. All right. And then here, okay, so now we're told that we're given this information. All right. We're given that the angle between the tangent and the chord is equal to the angle in the alternate segment. And so what we can then conclude is that this line QP is a tangent to the circle. So actually, we did not know that this was a tangent to the circle. So we just know that the angle between QPA is equal to the angle B. And this is technically the converse of what we have done above, right? So this is the converse. And so we see that we now we've got the conclusion and we're doing the opposite of what the Tan-chord was telling us originally. So here, if we were given that the angle between QPA is equal to angle B, then we can conclude that this line is a tangent to the circle. So it's important to know which results are true in both directions, and the Tan-chord theorem is one of them. Okay, so those were some important results. And then lastly, before we begin with some questions, I want to remind you about cyclic quadrilaterals. What is a cyclic quadrilateral? Who'd like to explain that to me? So here you can observe, while somebody is going to be responding in the chat box, we have a circle and we clearly have a quadrilateral with vertices A, B, C, D. So what is the definition of a cyclic quad? Okay, and we also had a question that was posted earlier. Someone asked in the first diagram, can you use the chord TC and use it to be equal to B? So let me go back in the first diagram. Can I use that? Okay. Yes, that's exactly what I explained in the other diagram. Okay, perfect. And now I'm going back to the chat box. We have a response here that says when all 4 points touch the circumference of the circle. Perfect. That is what I was looking for. All right, so that is a cyclic quadrilateral. It is a quadrilateral whose vertices actually lie on the circumference of a circle. So in particular, this diagram that you see here is an example of a cyclic quad, and likewise in the second one, right? So vertices of the quadrilateral. So I'm not sure why that didn't write. Let me correct that. Right, of the quadrilateral. So all vertices lie on the circumference of the circle. Okay, so that's what we're looking for. So let's look at this first result. So this first result tells you if you have a circle with a quadrilateral in this way, so you've got a cyclic quad, and if you know that the opposite angles, in particular here, A added to C, okay, sorry, apologies. Let me explain again what this table is doing. So here we're given the information once again. The next column is going to be the conclusion. So let me erase that because I was talking about the converse. So this is the conclusion. And in this column, again, we've got the reason. Okay, so we're given a cyclic quadrilateral, and if you have a cyclic quadrilateral, right, so we're given this, and if you have it, then you can conclude that opposite angles of the cyclic quadrilateral are supplementary, meaning that the sum of the opposite angles equal to 180 degrees. The second result that we have is that if you once again have a cyclic quadrilateral, but we've got this line extending to a point outside the circle, in particular it's going to E, then if this is the case, so once again you're given the cyclic quad, then you can conclude that in this situation that A is equal to BCE. So it's equal to the external angle. This is an angle outside of the cyclic quadrilateral. So this interior opposite, if you think of it, A is equal to the external angle of the cyclic quadrilateral. Now it turns out that the converses of these results are also true. So let's consider the converses. So that's what I was mentioning earlier. Right, so we'll call this let's call this A and let's call this B. So we're now going to look at the converse of A. Okay, so if we look at the converse of A, what is that going to state? So let's just say we're given some quadrilateral. Okay, so it clearly was not drawn perfectly. Nonetheless, so this is a quadrilateral. I'll label its vertices A, B, C, D. And if I know that the opposite angles here are supplementary, so if I know this, if I give you and I tell you that angle A plus angle D is equal to 180 degrees, then you can conclude that this is a cyclic quadrilateral, meaning that in particular, these points would lie on some circle, right? So this is a cyclic quadrilateral. So that's the converse. So think about it. In the first bit, you were told that it's a cyclic quadrilateral and you can conclude that opposite angles are supplementary, but here you are given that the opposite angles are supplementary and you conclude that it is a cyclic quad. Okay, who wants to help me write down the converse of part B? Converse of part B. You can just type the converse in the chat box and we'll go through it. So B says that if you're given a cyclic quadrilateral with one of the sides being extended to an external point E, then it is true that that interior opposite is equal to the exterior angle of the cyclic quad. So what is the converse? Right, so the converse is the following. So if I give you a quadrilateral, right, and we've got one of the sides going out like that, A, B, C, D, to some external point E, and I tell you that angle A is equal to angle BDE. Right, so if that's what you're told, A equals BDE, then we conclude once again that it is a cyclic quad. Okay, has everybody followed up to this point? I'm looking for some yeses, nos, so we get a feel for where's everybody at. Okay, great, wonderful. Thank you for the feedback. Everybody is following, I'm glad. All right, so those were two results and they're converses and we see that it is true. Okay, so there's one more result about cyclic quadrilaterals that I would like to bring your attention to. So I'm going to draw you a picture. I'm going to give you some information and I'm going to tell you what we can conclude. Right, so let's hope that my picture drawing skills are good enough, right? So this is what we're going to draw. Okay, how should I make it look? Okay. So I'll have it go like that, and then like that, and then like that. Okay. All right. So this is what I need to draw. This is B, this is C. Let's call that A, and let's call that D. So we've got A, B, C, D. And let's just say that I tell you that angle B is equal to angle C. So you're given this information. So clearly we have 4 vertices, A, B, C, D, but in particular, B equals C. Then what we can then conclude, because of the angles in the same segment, if you remember from the earlier results that would have been done in the previous lesson, is that this is actually ABCD is a cyclic quad. So this is the conclusion. So this implies, this is the implication sign, ABCD is a cyclic quadrilateral. So this is another way to determine if a given diagram is a cyclic quadrilateral or not. Okay, so keep these important theorems at the top of your mind. Okay, so know it. All of these things form, it becomes the machinery that you are allowed to use, right? So make sure that you can apply it in the relevant situations. Quadrilateral. Okay, got it. Spelt that. One more thing that we could also say is it is equivalent to saying that A, B, C, D is concyclic, meaning that its vertices lie on a circle. So that's some terminology that I'm just presenting you with. Okay, so just keep that in mind. Okay, so those are the results that I wanted to bring to your attention. And now we're going to look at some past papers, and we're going to try to solve as many questions as we possibly can. So you may need to have pen and paper out to work through the questions with me, and make sure that you type in the chat box to let me know what answers you are arriving at, because I'm going to work through it with you. Okay, so let's do that. I'm now going to share a different set of slides. Let me see if I can find it. That's not the one. Just give me a moment to get the correct one ready. Got it. Right, so this is what we're looking at. This is once again last year's examination paper. And we are now going to apply the results that we had just learned to answer this question. So firstly, let's absorb all of the information that we are now being presented with. So we're told that ABCD is a cyclic quadrilateral. So here are the vertices ABCD, and they lie on a circle, right? We're also told that AB, that line segment, and line segment DC are produced to meet at E. Okay, that's fine. Quick question. Is this line a tangent to the circle? The line drawn from the exterior point E, is it a tangent to the circle? Yes or no? No, wonderful. So that means we cannot use those results about the tangents. So keep that in mind, don't be tricked. Okay, so that's good, right? And then we're told that AD and BC are produced to meet at F. So let's go and look at the diagram. That's true. There is indeed another exterior point. So we've got 2 exterior points, but once again, observe that like E, the line segments that are meeting F are not tangents, okay? So again, we do not have tangents in here. Right, and then we're told that AFB, angle AFB, here we go, it's here, is 2x, DAB is 3x, and AED is x. So we've been given some angles that have been labeled in here. So we've got 2x, 3x, and x. So what's the question? The question says, determine, giving reasons, the value of x. Okay, so we want to find out what x is. Now observe, x, 2x, and 3x are all angles within specific triangles. All right, so if we had to look at specific triangles, who'd like to tell me what type of strategy we might want to use to answer, to solve for x? we've got these angles within triangles. Can you identify some of the triangles for me? You could just type in the vertices of the triangles that you'd like to bring my attention to. So I'm going to highlight one of them to get us started. So we can see that we have triangle ADE. And within this green highlighted triangle, we have one of the angles are x and the other angle is 3x. So that is known to us. There's also another triangle that we could bring our attention to, and it is triangle AFB. Again, we have 2x and 3x are angles within this, okay? And I see we've got quite a few responses in the chat box, so thanks for that. All correct answers. And there are a few other triangles, the smaller triangles, for example, BEC, and in particular here, we could also draw our attention to CDF, okay? So I was just tracing through to alert you to the triangles that we could work with. So what I think, okay, so this is the strategy that I'm going to use. We are going to try and work with the following triangle, the one that I'm highlighting. Let's work with this triangle, ABF, okay? We've got the 3x, we've got the 2x, and what we'd like to do is find out what is angle B2, because if we know what angle B2 is, and if we've got a representation or description in terms of x, then shouldn't we be able to use that the sum of the angles of a triangle equals to 180 degrees. So using that fact, we could then solve for x. Is everybody following the strategy? Just waiting for some yeses or nos, so I know whether to proceed or explain again. Wonderful. Okay, so everybody's following on the strategy, so we know what we're working towards. Okay, so let's get working. So what we have is a 3x, and we know that this is 3x that lies in a cyclic quadrilateral, isn't that so? So if I just draw your attention, that's B, A, C, D, and we've got 3x. Using the results that we had just gone through on the previous slide, if you know that A, B, C, D is a cyclic quadrilateral, what can we conclude? What do you know about the exterior angle of the cyclic quadrilateral? In this case, we know that C3 equals to 3x. Do you all agree? Because of the exterior angle of the cyclic quad. So that's what we're working with there. Right, so I hope that you all agree with that assessment. Let's take a look. Okay, great. So C3 is equals to 3x. Okay, so that's what we've got. But I want to get to B2, right? So if I know what C3 is, then let me bring your attention to something else. So C3 is equals to 3x, but let's look at what's happening at the C, isn't that so? Here is C. I've got the following happening. This is 3, 2, and 1. I'm just duplicating that part of the diagram. Okay. What do you know when you're in a situation like this? Do you remember your results about vertically opposite angles? So we see that C3 is vertically opposite C1. And so when they're vertically opposite in this way, don't we know that those angles are equal? So the conclusion here, if we follow through, is that C1 also equals to 3x because of vertically opposite angles. And that's the diagram to help you understand why that is true. Wonderful. Okay, so we've got that done. So let's go back to the original diagram and let's fill in our information to help keep track of what we know. So we know that this is 3x. I'm just going to use that pink color. We also know that this is 3x. But now look at the smaller triangle here. Right, so let's look at the smaller triangle where we have received a lot more information about the smaller triangle. In the smaller triangle BEC, I've got the x and I've got the 3x. What can I conclude? I can definitely work out B1 and then in place, of course, B2, but using some of the results about triangles, don't we know that the exterior angle of a triangle is equal to the sum of the interior opposites, right? So it is known that, okay, I'll write it down here so you can see it immediately, right? So there's a result about triangles that B2 is equal to E plus C1. This is nothing but the exterior angle is equal to the sum of the interior opposites of a triangle. So I hope that you're remembering all of these results that you would have gone through since grade 10. Okay, so let's keep that in mind. So then can you tell me immediately about angle B2? Angle B2 is equal to 4x. So that's important for us to keep note of. So we see that B2 is equal to 4x. Why is it equal to 4x? Because angle E was equals to x and angle C1 is equals to 3x. Is everybody following up to that point? Wonderful. I see in the chat box that you've already seen that B2 is 4x. You've gotten there. Perfect. Right, wonderful. And so that is what we wanted to do, isn't that? So the whole aim of highlighting the orange triangle was to say we want to find B2, and we found B2. So we're now on the home stretch, and we can then go ahead and write down or solve for x using the fact that the sum of the angles of a triangle equals to 180 degrees, because the sum of the angles of triangle ABF would be 3x plus, in particular in this case, 4x, as we had just seen, which was 4x. So it would be 3x plus 4x plus 2x equals to 180 degrees, and then we are able to solve. So let's write that down. 2x plus 3x plus 4x, got it. 2x plus 3x plus 4x equals to 180 degrees. But what's the sum of this? This is nothing but 9x equals to 180 degrees. What is the reason I could write down the first line? It's because of the sum of the angles in a triangle. Okay, so that's just the shorthand that you are allowed to use in school. And then, of course, we see that x is 180 degrees divided by 9, which gives you 20 degrees. So that means that what we wanted to solve for, which is x, is equals to 20 degrees. So I'm just going to quickly check the chat box. So there was there was a student who did say no. So I'll quickly review the strategy quickly before we move on. And then could D1 equals to B1? Sorry, there's another question. Could D1 equals to B2? Is that the case? Is D1 equals to B2? Correct. That is 100% correct because of the result on cyclic quadrilaterals. It is an exterior angle. Okay. So you could also use, there's different ways. This is one strategy, and you could have chosen to have worked with some of the other triangles that I highlighted. Okay, but for the purpose of time, I'm not going to go through the other ways, but make sure that you spend some time doing it and come to the same answer of 20 degrees. So just to highlight the strategy here, we restricted ourselves to working with A, B, F. And the idea was 3x was known, so angle A was known, angle F was known, so I wanted to solve for B2. So how did we find B2? We firstly used the property of the cyclic quadrilateral, and we saw that C3 is equals to 3x because it is an it is an exterior angle. Okay, so using the 3x from angle A, we see that C3 is equal to 3x. We then went on to observe, so we had that 3x, that C3 was vertically opposite C1. So then C1 is also 3x. And then utilizing triangle BEC, I see that I know angles x and angles 3x. So the exterior angle B2 is equal to the sum of the interior opposites, which is x plus 3x, giving me 4x. And then the home stretch, add 3x to 4x to 2x, which should sum up to 180 degrees because you're working in a triangle, and solve for the unknown, which is x. So I hope that that strategy was clear. Okay, so is everybody all on board with what we've done now that I've highlighted the strategy? Wonderful. Yes, so there's numerous ways of coming to the same result of 20 degrees. Okay, so let's go on to the next question. Great. All right, so here is our next question. Okay, and I'm glad that the person who previously answered no has now said yes. So thank you, Zintle. Right, so this question now says that we have a diagram, we have a center. So we have a circle with center M, and ABC are points on the circle such that AC equals BC. So we're told that AC equals to BC. So that is why we've got this line here to denote that those two line segments are actually equal. So observe that those are line segments, or technically they're chords, right? They're chords in the circle, but they are also the sides of the triangle ABC. So it's important to note because we've got the two sides are equal. Would like to tell me more about a triangle where two sides are equal? What type of triangle is it? Okay, so while you tell me that, let me read the rest of the information. We're then told that PA is a tangent to the circle at A. That is indeed true. Okay. PQ is drawn parallel to CA. PQ is drawn parallel to CA. So there's another nice thing happening in here. We've got parallel lines, and it's also part of a triangle. Look at triangle BQR. That's an important one for us to talk about. BQR. I hope you remember the proportionality theorem. Or also a consequence of the proportionality theorem, which is the midpoint theorem, because here we have parallel lines drawn within a triangle. So we need to check, I mean, are the sides divided in proportion, right? Okay, so we've got some responses in the chat box. Wonderful. Isosceles triangle. Yes, that's what I was looking for, isosceles. So we might need to utilize some information about this isosceles triangle. So let's keep that in mind. Okay. So we've got that bit, and we're also told that BC is produced and it needs PQ at R. BC needs PQ at R. Ah, there we go. So yes, we had seen that. So here is BC. It continues to R and there's PQ. Perfect, we can see that. And we're told that Q is equal to X. So let Q equal to X. All right, wonderful. So we're given this information. This angle is X. Right, so what do we need to find out? So we need to find out, determine, giving reasons for other angles that are also equal to X. Okay. Right, so let's pay attention to our diagram. What else is equals to X? We need to find 4 more. Right, so it was one of the important pieces of information here. Let me highlight this in blue, is that this was parallel to this. And now I've got this angle X, right? And I've got this parallel line. So do you remember corresponding angles? So we see, yes, perfect. Someone said it in the chat box, A1 equals to X. So let's write that down because of corresponding angles. A1 equals to X. I'll highlight it here above. A1 equals X because we had that AC was parallel to QR and its corresponding angles. So we've got that bit. So that is good. Then I now know that this is X. And remember we spoke about this isosceles triangle ABC. So because the side here opposite X is equal to this side, then clearly angle B itself must be X. All right, so let's highlight that. B equals to X because side AC equals to side BC. Okay, and you could have also gone on and explained isosceles triangle, talked about the properties, etc., to explain that. Okay, perfect. And then I see again in the chat box, we have students responding with the same conclusion. Excellent. And then we need one more side, right? Oh no, we need two more. Apologies, I'm getting ahead of myself. Okay. So we were told, what other information are we given? We said we have a tangent, right? So we've got a tangent PA at A. So let's keep track of that. I've got a tangent. Okay. So let me highlight a specific part of this diagram for you. So we've got AB. C, and then I've got a tangent going to P, right? And of course there was a circle, right? So there's a circle that's going through here. So my diagram. So imagine that circle. So can anybody see anything emerging where we can apply a result that we had discussed earlier? Can you see that we can apply the Tan-chord theorem? Yes, someone asked, can I also say that A2 is equal to Q? Yes. Well, the reason why A2 is equal to the value X is because of the Tan-chord theorem in here. So this is A2, right? This is A2. And we know that that is X. So by the Tan-chord theorem, the Tan-chord theorem tells you, there we go, that we can conclude this. So whenever I have this situation happening, we can conclude that angle A2 is equal to X. Is everybody clear on the application of the Tan-chord theorem? Which was the tangent and which was the chord? The chord is AC, the tangent is AP, and here is the angle in the alternate segment, X. So we see that A2, the angle between the tangent and the chord, is equal to the angle in the alternate segment. Everybody clear? I'm just looking at the chat box. Perfect. Yes, someone says it's equals to B. Wonderful. Right. So we now have another angle that's equal to X, and that is A2. So let's make a note of that. A2 equals to X because of the Tan-chord theorem and that highlighted diagram. All right. And now we need one more. And I see there was someone else explaining something in the chat box about alternate angles. So which angle are we going to obtain due to alternate angles? Which one? Which other angle due to alternate angles equals to P? Wonderful, you've answered. It's P. So let's highlight this bit. So it turns out that this angle here, P, wrong color. P here. So we've got our parallel line and we've got this line segment AP. So clearly using A2, we see that this is an alternate angle. And so therefore A2 equals to P using alternate angles because AC is parallel to QP. Okay, so that's the fourth one that we have found. Wonderful. Right, so we have that P equals X because of alternate angles. Okay, I'm quite happy with that. I hope everybody's followed. Right, and then we have to prove that APBR is a cyclic quadrilateral. Okay, so let me just try and remove some of the highlighted bits so we could bring our attention to APBR. I'm going to try and highlight that. PR, sorry, ABPR. So here is A. Okay, we need B, which is highlighted. We've got P and we've got R. Okay, so what does that look like? A, B. Okay, so it's this. So often it works out well when you have a page that you could rotate around, but unfortunately I can't do that, so you find me moving my head. So I'm just trying to highlight this neatly. So I hope you can see what it is that I need you to see. Okay, so can you see that picture? APBR or ABPR, right? So it's this yellow bit. And the question is this a cyclic quadrilateral? And if so, why? What makes it a cyclic quadrilateral? So do you remember the result that we had gone through earlier? Let me try and go back. Here we go. Here it is. Doesn't this butterfly type picture here that I've drawn look similar to what we had in the previous, in the question we're currently looking at? So the question is, do we have that the angles are equal when observing in that same segment? Okay, so we need to go back and verify. If this is true, if our butterfly satisfies this property, then we can conclude that A, B, C, D are concyclic, and hence it's the same as saying it's a cyclic quadrilateral. Does everybody follow the strategy? Oh, angles in the same segment, converse. Yes, that's precisely what we want to do. Wonderful. Let's go back to the question. So we've got our butterfly picture. There it is there. And observe that what we require is already there, right? It's already there. So we've got X and we've got X, angles in the same, so angles in the alternate segment as somebody had, in the same segment, the converse of it. So clearly, right, so they're in the same segment, we've got X and X, B is equal to P as we had proven in 9.2.1, there it is here, B is X and P is X. And so therefore, using the result that I had just shown you, we can conclude that therefore ABPR is a cyclic quadrilateral. Okay, so we see, so how would you have written that down? You would have explained that P equals to B. This implies by the result that I had shown you that ABPR is concyclic by that result. And therefore, this is the same as saying that ABPR is a cyclic quadrilateral. Okay, that's good. And you could provide a reason that the student had explained as well. It is the converse of the angles in the same segment. So that is a reason. Right? Converse. Angles in same segment. Okay, so I hope that everybody is happy up to that point. Are there any further questions? So it's nothing but us utilizing this result that was in the previous page, right? So this is what we're doing. We had the butterfly and we verified that the angles were the same. Okay, I hope everybody's all good. We've now got 9.2.3, and this is what I'm going to cover, and then we're going to end. So we are required to show that BA over BQ. Right, so let's go and remind ourselves of where all of these things lie. BA, which is this side, over BQ, over the bigger side. So we've kind of got that length over that length. So going that way must be equal to BC. Right, so let's look at where's BC, which is this side, right? Over QR. Where's QR? Ah, QR is this side. Okay, so that's a little weird. So, but think about it. Can't we conclude something pretty similar? What do we know in here? What result would you like to apply to get out one ratio being equal to another ratio? Because that's what we have. We have a ratio on the left and I have a ratio on the right. Okay, and in particular, we've got BA over BQ. What do you know about that? What is it equal to? So we have a response. Similarity rule, proportionality theorem. Wonderful, proportionality theorem from the previous lesson. So because we know in here, so let's go back to here. Let's remind ourselves very quickly. Right, so by the proportionality theorem, right, a line drawn parallel to one side of a triangle divides the other two sides proportionally. So that's what we're going to utilize. That's the result. So we've got a line AC and it is clearly, we were told that it is parallel to QR. So I'm now looking at triangle BQR. Okay, so let me write that down. In triangle BQR, remember I had highlighted those vertices at the beginning. There it is in green, BQR. So that's a triangle, the big triangle I want to look at. We see that AC is parallel to QR, right? So we have a line drawn parallel to another side. I said AC is parallel to QR. I hope that's what, is that correct? Yes, it is. AC parallel to QR. So what can we conclude? That it divides the sides in proportion. So in particular, because of this, we can then say by the proportionality theorem, we have that the following ratio must hold true, that BA divided by BQ would be equal to BC divided by BR. I hope everybody agrees. So let me remember that as I scroll down, BA over BQ is equal to BC over BR. BC over BR. BC over BR. So we have a ratio, but it is not the ratio that we require. So we've got BA over BQ, as you can see, we've got it there, and we've got that it's equal to BC, not over QR. In place of QR, we have got BR. So is there a way for us to see how these things are related? That's the question. Can anybody see if BC and QR are related in any way? So we want to pay attention to, so this is, I'm sorry, QR and BR. Right, so this is our problem. This needs to be QR for us to be done, but it's not, or is it? So let's check. So here is BR, and here is QR. Can anybody perhaps see how these two sides are related? Triangle is an isosceles. Wonderful. Yes. Observe that angle Q is equal to angle B. So once again, these two sides must be equal. Okay, so let's make a note. Observe that, okay, we could just say that angle BQR is isosceles. Observe that triangle BQR is isosceles. So this implies, because we know that Q equals to B, since Q equals V, we have that BR, side BR equals to side QR. And that resolves the situation. So therefore, BA over BQ equals to BC over QR. And that is precisely what we were required to show. Okay, I just got a notification that my internet connection was unstable, but I hope everybody caught that. So this is where we end our lesson. So I hope that everybody had benefited from the problems we had answered together today. It was a pleasure to spend the afternoon teaching you. And this recording would be available on YouTube, as well as the notes. We will have this mailed out to you. So if you missed anything or want to recap on anything, you will have a further opportunity to do so. Thank you once again for joining me on this Thursday afternoon. And please don't forget that we have upcoming lessons. There are 3 more lessons every alternate Thursday. So I look forward to engaging with you then. All right. So thanks, everyone, and goodbye.